Hello. Is it okay now?
Yes, it is visible. It is okay.
Thank you. Thank you. So, good evening, all of you. So, the next topic, which I am going to give a brief idea about nonlinear programming problems. So, in the first lecture, we have discussed a few concepts of linear programming problem. I hope that you might have understood some of the important concepts involved in non-linear programming problems. So that why how simplest method work and what are the various points which are there in tables and other concepts related to linear programming problems. So now let us talk something about non-linear programming problems, right? So, have you ever discussed? Have you ever, in this work, in this in this program, have you ever deal with this lecture on nonlinear programming problems? Yes or no? No, not till now. Yes, Brinda. Okay. So, I in the morning I told you that whenever we formulate a journal model for a optimization problem, we always framed like this: minimum or maximum of fx subject to ggx less than equal to 0, j from 1 to m, right? So here this function we have to minimize subject to m number of constraints. So suppose this problem, we are setting this problem as p. This function f is from Rn to R. That means we are having x as number of x is variable and number of variables are n, right? And all gjs are basically are also from Rn to R, j from 1 to m, right? So number of variables here are n, number of variables are n, and number of constraints are m. Now the question is that linear programming problem are the simplest optimization models, and it is very easy to deal with linear programming problems, right? We have seen few algorithms, right? But the non-linearity in optimization problem may be very high, maybe of complicated problems, right? Then how we can deal with such problems? Of course, we cannot have single method to deal all the nonlinear programming problems, but there are some problems which we can handle easily using some of the techniques analytically. However, some of the online softwares are available by which we can easily find out the optimal solutions. But there are some methods analytically also by which we can solve some nonlinear programming problems. Some specific, not all, right? So before going to deal with such optimization problem, let us first discuss few concepts. So first of all, we deal with convex functions. Why convex functions? Why not some other functions? This we will discuss later on. First of all, we focus on the basic definition of convex functions, and then we will then we will see that why convexity is required. What is the importance of convexity in nonlinear programming problems? Right. So first of all, we deal with convex functions, right? So suppose you have a S subset of Rn, which is a convex, which is a non-empty convex set. Convex set, we already know what convex set is, non-empty convex set, right? Let, okay. So then, so this is let this be a convex, this be a non-empty convex set. Okay, then f from S to R is said to be convex function, right? If this inequality hold. So what this inequality, what this, you might be thinking that this is very different inequality. So if this inequality is holding for all x1, x2 in S and for all lambda between 0 and 1, then we say that the given function is a convex function, right? For example, you can see a simple example. For example, you are seeing function from R to R, and the function is simply suppose fx equal to mod x. The simple example I am taking mod x, right? Now if you take f of lambda x1 plus 1 minus lambda x2 in this case, right? So by the definition of f, it will be mod of lambda x1 plus 1 minus lambda x2, mod of this, which is less than equals to mod of lambda x1 plus mod of 1 minus lambda x2, which is equal to lambda is non-negative from here, so if lambda can be taken out, mod of x1 plus 1 minus lambda mod of x2, and this is nothing but lambda of fx1 plus 1 minus lambda of fx2. So this means what? This means this definition holds. So we say that this mod x is a convex function. Mod x from R to R is a convex function, right? So what does this definition means geometrically, right? Now let us try to visualize this thing also. So suppose you are having this shape of the function. Suppose you are having this y equal to fx, right? Suppose this is y equal to fx. Suppose you are having any 2 points, one point here, say this point is x1, and suppose this one point is here, suppose this point is x2. You take any point x in between x1 and x2, right? The coordinate of this point will be what? X1 comma fx1, and the coordinate of this point will be x2 comma fx2, right? Now you join the chord, right? Now this point x, if you take if you draw a line perpendicular to x-axis passing through this point x, so this point will intersect here and will intersect here. Suppose this point divide this line segment in the ratio, suppose 1 minus lambda is to lambda. So this x will be lambda x1 plus 1 minus lambda x2, right? This is very simple because if it ratio is 1 minus lambda is to lambda, so this x will be nothing but this. And the same ratio will be governed here also, 1 minus lambda is to lambda. So you can find out the coordinate of this point also. So this will be x, suppose this is y, right? So this y will be nothing but this y dash, you can put y dash. This y dash will be nothing but again the CLC of these 2 points, which is nothing but lambda fx1 plus 1 minus lambda fx2. However, the coordinate of this point will be x comma fx, right? Because it's lying on the graph of the function. So you can see that if this point is A, this point is B, this point is C. So this AB here in this case, AB is strictly less, but it may be equal to also AB is less than equal to AC. You can see now AB is this length only, this height only, and AC is the entire height. So the AB is always less than equal to AC. And what is AB? AB is y coordinate. The y coordinate is fx, which is less than equals to AC. AC is y dash, and y dash is lambda fx1 plus 1 minus lambda fx2. So what does this means? This, or what is x? X is simply this point, right? X is this point. So that means this definition is true. So geometrically, how can we say the given function is convex or not? this can be illustrated now by this simple drawing, because you can see that you draw the graph of the function, take any two arbitrary point on the graph, join the chord. The chord always lies above the curve, right? You take 2 point, 1 point here, 1 point here, join the chord always lies above the curve. Take 1 point here, 1 point here, join the chord lies above the curve. So above or on the curve, if it is a straight line, if it is a straight line, it lies on the curve also, right? So if you take any two arbitrary point on the graph of the function, join the chord. If chord lies above or on the curve, then we can say that the given function is a convex function, right? So this definition geometrically means this thing, that the chord is lying above the curve or on the curve. Now using this visualization, we can easily predict that which functions are convex or not. For example, you can suppose you take mod x, right? Mod x. This is the graph, right? Y equal to mod x. You take 1 point here, 1 point here, join the chord lies on the curve. You take 1 point here, 1 point here, join the chord lies above the curve. So this is clearly a convex function. Now you take, suppose y equal to, say, e raised to power x, right? E raised to power x. So this is the graph of e raised to power x, right? Now you take 1 point here, 1 point here, join the chord lies above the curve always. So this function is also a convex function. Now suppose you take y equal to, say, e raised to power minus x. This is something like this graph. So again, you take any 2 point on the graph, draw the chord lies above the curve. So this function is also a convex function. Now you take, say, y equal to x cube. You take y is equal to x cube, right? So the graph is something like this. Now you take 1 point here, 1 point here, join the chord. Chord sometimes lies above the curve, sometimes lies below the curve. So this is not a convex function. Are you getting my point? Right? So yes, Satyendra, you are right that if this inequality is reverse, if this instead of greater than equal to, if it is if it less than equal to, if it is greater than equal to, then the function will be a concave function. Yeah, that's correct. So in fact we can say that a function is concave. We can say, Satyendra, we can say the function f is concave. Function f from S to R is concave if and only if minus f is convex. That means inequality is reversed, right? So we have examples of convex functions also, concave functions also. You simply multiply these functions, mod x or e raised to power x or e raised to power minus x by -1. We can easily say that these functions are concave functions, right? You can see here, suppose you are taking this function here. Suppose you take y equal to log x, right? So if you take y equal to log x, is something like this function, right? So if you draw the chord here, take any two arbitrary point, join the chord lies below the curve here. So it's a concave function. So this is a concave function. So for concave function, you take any two arbitrary point on the graph of the function, join the chord always lies below or on the curve, right? So this function x cube here is neither convex nor concave, because this chord sometimes lies below the curve, sometimes lies above the curve. So we cannot say anything about this, right? Uh, what about X3, Satinder? What you want to say? Okay, okay. Now, for a single variable function, it is easy to not always easy. Drawing a graph of a function is also not an easy task always, right? And if it is a two variable function or three variable function or 10 variable function, then the things will become complicated. So the question is that if we have a complicated function of maybe for three variable or two variables, how we can say that it's a convex or not? Is there any property of the convex function by which we can ensure that the given function is convex or not? Yes, we have. So we will discuss that property first of all, right? So the properties of convex function is something like this. So if we are doing for convex function, the same way we can go for concave functions also, because we know that uh, f is f is concave if and only if minus f is convex, right? So if we have an idea of convexity, properties of convex functions, the similar lines we can go for concave functions also, right? And if these inequality hold in strict sense, right, it is strictly less or strictly greater, then the functions are called strictly concave or strictly convex, right? That means in those cases the graph is always above the curve, not on the curve, for strictly convex. For strictly concave, graph is always, chord is always below the curve, not on the curve, right? So that is strictly concave, right? So the properties of convex function is, first property of convex function is that convex function may not be differentiable. A convex function may not be differentiable. It is not necessary a convex function is always differentiable. We have a counterexample. For example, you can take f from, just now we have taken f from R to R, and function is mod x, right? This function is convex but is not differentiable at x equal to 0. Okay, next. A convex function is always continuous in the interior of its domain. So that is another property. In if you say not interior, if it's the boundary, interior may it is always convex, it is always continuous. But if you see as a whole, the function may not be continuous, right? For example, if you take this example, suppose function is up to here, it is something like this. From -2 to 2, it is something like this, right? And then at 2, it is suppose something here. So you can see that this function is convex, but it is not continuous at x equal to 2. Suppose this graph is y equal to x square. So this function is convex, right? But at this point, but at x equal to 2 value, suppose 4. Suppose this point is 2, uh, when 2 is 4, okay, 2 is 6, suppose. Okay. So the in general, if you're not talking about the interior, if we're talking about in general, so function may not be convex, function may not be continuous also. Now the sum of convex function is also convex, right? Sum of two convex functions is also convex. In fact, if f is convex and alpha is greater than 0, alpha belongs to R, then alpha time f is also convex. So these are some basic properties of convex functions. There are many more, but I am just briefing you the important properties, right? Those who are interested to learn other things of convex functions, they may refer to some PDFs or some books which is available, and they can see these convex functions and their properties, right? And they can have a feeling of more about convex functions, right? Now if your function is twice differentiable, right? So I am dealing with a very strong property of convex functions, which will be helpful in determining whether a given function is convex or not, right? So that important property is basically based on the Hessian matrix, right? That result is something like this: that let S be a non-empty open convex set in Rn, right? Let f from S to R be twice differentiable. Please, if you have any doubt, please discuss. Satinder, what is your doubt? X3 we cannot say I am right. What is X3? X3 means what? Hello? Okay. Oh, X cube, you want to say. Yeah. X cube I already explained, right? Satinder, X cube is neither convex nor concave. It is neither convex nor concave, right? Okay, okay. Okay, thank you. So let us suppose this is twice differentiable. Sorry, twice differentiable. Okay, twice differentiable on S. Then F is convex if and only if Hessian matrix of Fx is positive semi-definite for all x in S. Right? Now, this is a very important property of convex functions. I am not going to prove it here. I am just illustrating you that what this property signify and how it is helpful in determining that whether a given function is convex or not. Right. So, but the limitation of this is that it should be twice differentiable. If it is not differentiable at all, then we will go for by the basic definition of convex function. That is this definition. This definition will be helpful in determining whether a given function is convex or not in that case, if it is not differentiable. But if it is differentiable, then we have few concepts by which we can say that whether a given function is convex or not. Okay. Now, first of all, what do you mean by positive semi-definite? This have two things, positive semi-definite, first of all. So, and what do you mean by this del square of fx, right? So, if you have a function from Rn to R, first of all, let us try to understand these two things, and then we will go by one or two examples and then further. So, a function you have from Rn to R, then del of fx is simply at a point x is simply del f by del x1, del f by del x2, and del f by del x, right? At this point x. This is called gradient of f at x, right? This is a vector in Rn, right? Now, when you take gradient square, that means gradient of f, right? And that simply gives you a matrix which we call as Hessian matrix. That means del square f by del x1 is square, del square f by del x1 del x2, del square f by del x1 del xn, del square f by del x2 del x1, del square f by del x2 square, and del square f by del x2 del xn. And similarly, it is del square f by del xn del x1, del square f by del xn del x2 by del xn square. This is a partial derivative, right? All these are double partial derivative, and this is a matrix of order n cross n. So this matrix is basically called Hessian matrix of f at x equal to x, right? If it is x bar, then it is x bar, right? So so this Hessian matrix is a square matrix of order n cross n, and this is basically of this type. Are you is it okay? Now, what do you mean by positive semi-definite? When the matrix A is set, this is a matrix, right? When a matrix set to be positive semi-definite, so let us see that thing also. Suppose A is a matrix of order n cross n, and A is symmetric also. So A is called positive semi-definite if X transpose AX is greater than or equal to 0 for all X in Rn. So if this property hold, then we say that the given matrix is positive semi-definite. And the important test to see that whether given matrix is positive semi-definite or not, so that means that is all the eigenvalues of A must be greater than or equal to 0. So if all the eigenvalues of the symmetric, because it is symmetric, so all eigenvalues are real. So we can talk about greater than equal to or less than equal to, right? And since all the eigenvalues if are greater than equal to 0, then we can say that the given matrix is positive semi-definite, right? So so now if you have a function of 2 variable or 3 variables or 4 variables, and you want to see whether given function is convex or not, you can find this Hessian matrix and find all the eigenvalues of Hessian matrix. If all the eigenvalues are greater than or equal to 0, then we can say that it's a convex function. Because eigenvalues are positive or greater than or equal to 0 means positive semi-definite, and that by this property we can say that the given function is a convex function. Right? Right? Is it clear? I hope that you are able to understand what what I try to say, right? Brinda is getting my things. What about others? Okay. Okay. Okay, Satyendra. Okay. So let us take one simple example. F from R2 to R, and suppose fx1 x2 is simply suppose 2x1 square minus x1 x2 plus 4x2 square minus 6x1 minus 4x2. Yeah, plus 4x2. I have taken one example. Now I want to see whether this function is convex or not, right? Similarly, I can go for a 3 variable or 4 variable problem as well to visualize whether that function is, to check whether that function is convex or not, right? So what is the Hessian matrix of this F? So that will be del square f by del x1 square as per the definition of Hessian matrix, del square f by del x1 del x2, right? Del square f by del x2 del x1 and del square f by del x2 square, right? So this will give you 4 minus 1 and this is 8. Now you can easily see that sum of eigenvalues is trace. It will be having two eigenvalues, right? So sum of eigenvalue is trace, which is 12, and product is what? Product is 32 minus 1, that is 31, right? You have not to worry that eigenvalues are real or complex in this case because it is symmetric. So eigenvalues will definitely be a real eigenvalues, right? Now both lambda are, because product of lambda is positive, so both lambda are either positive or both lambda are either negative. So negative, if both are negative, then sum cannot be 12. It will be negative, right? So that means both eigenvalues are positive. And both eigenvalues are positive means it is positive semi-definite, and this implies that a function is a convex function. So this implies lambda 1 and lambda 2 both are greater than 0, and this implies f is convex. Because lambda's positive means what? Lambda positive means it is Hessian matrix is positive semi-definite, and that means function is convex. Clear? Right. So now let us come back to our original problem on which we were discussing this nonlinear programming problem. So I asked you that why convexity? Why not? Why we are so giving so much importance to convex functions? See, we have some conditions. If a nonlinear problem satisfies those conditions, then we are able to find out the optimal solution of this problem analytically or mathematically. And those conditions are basically the convexity of the objective function and the constraints. If the objective function constraints all are convex, then we are able to find out the optimal solution of such problems. And these conditions are basically given by Karush, Kuhn, and Tucker, and that's why we are calling it Karush-Tucker conditions. What are those conditions? So let us try to see what those conditions are. First of all, what is a necessary condition, and then we will see the sufficient conditions. So these are basically Karush-Tucker conditions. First, we will see necessary conditions. See, like you are having a function from R to R, right? I'm just giving you a simple example. You are having a function from R to R, right? And function is once differentiable, suppose. And suppose x1 is a point of local maxima or minima. So what is the necessary condition for this point to be a point of local maxima and minima? The derivative of function at a point x bar must be 0. We all know. This is in 12th class, right? 11, 12th classes, we have already studied this. If functions from Rn to R, for example, and without any constraint, then we are, and xy is a point of local maxima minima, then gradient of fx bar must be 0. Right? So these are the necessary conditions. Similarly, if we have a constraint optimization problem like this problem P, which is a constraint optimization problem, it's a constraint optimization because constraints are involved, right? So in this case, what is a necessary condition? How we can say that if a point x bar is a point of local maxima or minima, then what are the conditions which it should satisfy, right? So what are those conditions? Let us see. For constraint optimization problem. Okay. So what are those conditions? Let us see one by one. So I'm simply giving you a idea. So statement of the theorem is something like this: that let x bar be a local minimum point of the problem P. Problem P is the above problem, the general nonlinear problem, right? At which the basic constraint qualification holds. Then there exist multipliers called KKT multipliers lambda I bar such that the following condition holds. So what are those conditions? First condition is gradient of fx bar plus summation I from 1 to m lambda I bar gradient of gi x bar equal to 0. First condition. The second condition is gi x bar should be less than equal to 0 for all I. This is second condition. The third condition is lambda I gi x bar should be equal to 0 for all I again. This is third condition. And lambda I, this is bar, lambda I bar should be non-negative for all I. It's the fourth condition. So these are basically those conditions. You might be thinking that, you might be observing that this is very complicated, but it is not actually. Let us try to see quickly. See if you see this constraint, this constraint. If you see this constraint, so this is a feasibility condition. Right? Of course, point must be feasible, right? This point x bar must be feasible. Then only we can talk about minima or maxima. For feasibility, this must satisfy all the constraints, right? This is called complementary slackness condition. This is called non-negativity restriction on KKT multipliers, or non-negative condition on KKT multipliers, right? On KKT multipliers. KKT multipliers. Right? And this, the first condition, which is important condition, this means that gradient of f at x bar, is can be expressed as some linear combinations of gradient of gi x bar. It is sum, right? So that means the gradient of f at a point x bar, which is a point of local minima, is always expressed as some linear combination of gradient of gi at x bar, right? So if a point x bar is a point of local minima, then there always exists some lambda bar, right? Such that the following conditions hold. This is necessary condition. But we are more interested to find out that what are the conditions which should be satisfied, so that we can say that that point is a point of local maxima, because we are basically interested in solving a problem, right? So to solve a problem, we need sufficient condition. What is sufficient KKT conditions? So let us see what is sufficient KKT conditions. Sufficient conditions, right? So sufficient condition is quite simple. Basically, uh, let x bar and lambda 1 bar, lambda 2 bar, and so on, lambda m bar and bar satisfy conditions 1 to 4 above, right? These KKT conditions, these conditions. And if f and gj's for all j, gj's for all j are convex, then x bar is the global minimum point of the problem P. Minimum point of the problem P. Right? So this is your sufficient condition. So now the convexity plays an important role here. This convex functions, right? This plays an important role here. If you are having convexity, right, and then and these four conditions are satisfied at a point x bar lambda bar, then the point will be the global minimum point of the problem P. Is it clear? So basically, convexity is required to to say whether a given point is uh, global minimum or not. But nowadays, people are trying to relax this condition. I am not going to much deeper to this concept. I'm just giving an idea to you that nowadays people are trying to relax this condition, that why only convex, why not some other functions which we can see and which we can visualize, and by which we can say that it is the KKT conditions are sufficient. So yes, there are some functions like pseudo-convex, quasi-convex, invex functions. These are the functions are there in the literature, by which we can see that for those functions also, which is a wider class of functions, these functions may not be convex, but for these functions, KKT conditions are even sufficient. Convex functions are the simplest form, right? Like linear programming problems, right? So that's why we first discuss with convex functions and then try to see some generalizations of convex functions. So pseudo-convex, quasi-convex, invex, these are all generalizations of convex functions, right? So let us see one example based on this. So that the things will be clear to you. Let us see one simple example. Okay. So suppose you want to minimize f equal to 2x1 square plus 2x2 square. I am taking a simple example to make you understand that what do you mean by this, right? Subject to, suppose x2 less than equal to 8 and x1 plus x2 less than equal to 10. Now, first of all, we have to check whether this function as well as all constraints are convex or not. Then only we can apply KKT condition to find out the optimal solution of such problems, right? So for f you can find out Hessian matrix, right? For f, what is Hessian matrix of f? There's simply 4 minus 2 minus 2 4. And again, by simple calculation, you can see that the eigenvalues of this matrix all are greater than equal to 0. This means it is positive semi-definite. by the same uh, reasoning which I told you earlier, positive semi-definite, and this implies f is convex. Now, if you see first constraint is G1, which is x2 minus 8 less than equal to 0. And the second constraint G2 is basically x1 plus x2 minus 10 less than equal to 0. This is the second constraint. And both constraints are linear. So linear functions are always convex. So hence convex. So we can see that f as well as all constraints are convex. So it is a convex programming problem. And hence the KKT conditions become sufficient. So now only thing we have to find out, we have to see all these four conditions, right? So the first condition is what? Gradient of f at x bar plus summation I from 1 to m here is 2. Number of constants are 2. Lambda I gradient of gi x bar equal to 0. What does it mean? This means it is 4x1, right? Minus 2x2. Then it is 4x2 minus 2x1 plus lambda 1. G1 gradient is 0, 1, right? And G2 gradient is what? 1, 1. And this should be 0, 0. So this give you what? 4x1 minus 2x2 plus lambda 1 plus lambda 2 should be 0. And the next constant is minus 2x1 plus 4x2, right? Yeah, Satyendra, you can see that this is a line x2. Forget about inequality. G1 is what? X2 minus 8, right? And x2 minus 8 is a straight line. You can see that straight lines are always convex because you take 2 point, it will lie on the line itself. The chord always lies on the curve. So it's obviously convex, right? In fact, these lines are convex as well as concave. Similarly, x1 plus x2 minus 10, if you see, so this is also convex. If you find the Hessian matrix, it is 0, 0, 0, 0, right? Null matrix, whose eigenvalues are 0, 0. So it is greater than equal to 0. It is positive semi-definite, hence convex. From there also you can see, right? Is it clear? Okay. So here lambda 1 will not come. So because it is 0, right? So this is plus lambda 1 plus lambda 2 equal to 0. These are first two conditions. Next condition is basically from the feasibility. Feasibility conditions are what? X2 less than equal to 8 and x1 plus x2 less than equal to 10. These feasibility conditions. What is the complementary slackness condition? That lambda 1 times gi equal to 0. So lambda 1 first g1 is this equal to 0, and lambda 2 times x1 plus x2 minus 10 equal to 0, and lambda 1 lambda 2 must be non-negative. So a point will satisfy these conditions will be the global minimum point of the given problem, right? Now, how we can solve it? We can solve by making four cases. See, by these two, we can see either lambda 1 is 0 and lambda 2 is 0. This is first case. Lambda 1 is 0 and x1 plus x2 minus 10 is 0. Second case. Third case is x2 minus 8 equal to 0 and lambda 2 equal to 0. Third case. And the last case is x2 minus 8 equal to 0 and x1 plus x2 minus 10 equal to 0. So using these four cases, you can easily solve because other putting these values in other constraints will easily simplify this thing. And at one point, at least you will get 1 point where all the conditions are satisfied, and that point will be the global minimum point. In this case, it is obtaining when lambda 1 equal to 0. It is this point, x1 equal to 17 by 4. You can check x2 equal to 23 by 4, and lambda 2 is basically 13 by 2, and lambda 1 is 0. This is the global minimum. So in this way, I am just giving you idea that if you have a non-linear programming problem and you try to visualize this analytically, that whether we can find out the optimal solution or not. So yes, we have some methods in the literature, but that is specifically meant for some special type of NLPs, not for all NLPs. We cannot solve all the type of non-linear programming problem by a single method, right? People are working that how we can make a special class of problems by which we can apply some technique and we can solve it, right? So this in this lecture we have seen that the convex functions, their properties, and how convex functions are important to find out the optimal solution of some of the nonlinear programming problems, which are convex programming problem basically. So Karush-Kantakar condition will be helpful to visualize, will helpful to see that how we can find out the optimal solution of a given nonlinear programming problem, which is convex programming problem, right? So any questions in this? Any questions, please? Any question, Rupesh? Any question?
Yeah, participants, if you have any question, you can write in the chat window. इसका वो बंद करो, म्यूट करो, अनुराधा म्यूट करो माइक को. Professor Gupta, if possible, we can take a break of 5 minutes so that
Okay.
participant can also get freshen up. And after 5 minutes, you may start your another lecture.
Okay. Thank you.
Yeah. So participants, we will be back again at 5:05. We will be having a break of 5 minutes. Participants, can you hear me? Okay, good. So I again welcome Professor Gupta for this another lecture from 5 to 6. And before Professor Gupta starts his lecture, I would like to make one announcement uh, about regarding the quizzes. We will be having one quiz today only and another quiz tomorrow. So I'll be sending one email regarding this to you. We have fixed a slot from 6 p.m. to 11:55 p.m. today. Means today you will be having 6 hours to choose any time slot of 1 hour in between 6 to 12. And through Canvas platform, you can attempt quiz number 1. Okay, but be remember that you will be having 1 hour. Once you will start the quiz, your time will start counting from that moment, and after 1 hour, the link, the quiz will be closed. Okay, so you may choose any time slot today from 6 p.m. to 12 p.m. as per your convenience to attempt the quiz. Similarly, tomorrow also we will be having similar uh, 6 hours to attempt the quiz. Let's say from 9 to 3. So 9 a.m. in the morning up to 3 p.m. in the afternoon. Okay. So again, this time slot will be for for 1 hour for each quiz. And to qualify the quiz, we will be taking best of two, and 40% marks is required to qualify the quiz. Okay. So we will be taking, you will be attempting two quizzes. We will take best one of these two, and best one, if you are securing 40% marks, then you will be able to get the certificate. Okay. No, tomorrow will be from any slot from 9 a.m. to 3 p.m. Okay. You may choose any slot as per your convenience from 9 a.m. to 3 p.m. Long question, because if you have internet connectivity problem or some other issue, you have some other important work. So I am giving this freedom to all the participants. They can choose any 1 hour slot in the time period given by us, and then they can solve the quiz. But again, remember, you will be having 1 hour only. That 1 hour you are free to choose any 1 hour between the time slot which we will be giving to you. So today it is from 6 p.m. to 12 p.m. Means 12 night, and tomorrow it will be 9 a.m. to till 3 p.m. in the afternoon. Okay. So I'll be sending the mail also, so that you can get all the information in the email also. So now Professor Gupta has again joined with us. Professor Gupta, I request you to please start your lecture. Over to you, Professor Gupta.
Okay, thank you. Thank you, Rahulji. My voice is audible? Voice is audible? Hello?
Yes, Professor
Yes.
Gupta, you are
Okay,
audible.
thank you. Thank you. So now the next lecture is based on gradient based methods in optimization techniques. So see, of course, as I told you earlier, that when we solve a non-linear programming problem specifically, so based on the non-linearity involved in the problem, there is no unique method to solve such problems. And also, all the problems you cannot solve analytically because of the complexity of the problem. So there are some numerical algorithms available in optimization by which you can solve at least an approximate optimal solution of a given problem. Of course, we cannot find the exact solution using these techniques, but at least we have some technique by which we can find out the best possible solution of the given problem. So we have some gradient based methods, or we have some direct search method by which we can find out the optimal solution of a unconstrained optimization problems. We have some techniques for constraint optimization and constraint. If you do not have any constraint involved in the given optimization problem, we call it unconstrained. And if there are some restrictions involved in the variables, we call it constraint optimization problem. So there are some such techniques are also involved, are also there to solve unconstrained optimization problem as well as for constraint optimization problems. So before going into the into these methods, let us first of all try to understand that what a common basic scheme is basically for a given problem. So here, first of all, we are focusing on focusing on some uh, unconstrained optimization problem, right? First of all, unconstrained optimization problem. So what is unconstrained optimization problem? That means you are simply minimum of fx and x is in Rn. There is no restriction on the variables, right? So you have to minimize f subject to x is in Rn. X is any point in Rn, right? You have to minimize it. So for this problem, for the simple problem, how we can optimize it, or how we can find out some such techniques. So first of all, we are having what is the basic scheme. So basic scheme for this problem is basically, or for any optimization problem, is basically is xk plus 1 equal to xk plus alpha k dk, right? Now what this scheme means, basically, you start with some initial guess, x0 for example, and you go to x1, right? You start with x0 for example, and you go with to x1, sorry, okay, you go to x1. Okay, now going from x0 to x1, there are many directions, right? There are many directions. uh, so this is basically dk, which give you the, which is the, in which direction we should go, so that we can find the value of xk, we can improve the value of our xk, right? In which direction we should move, right? So suppose the direction is d1. D1 is the direction in which we should move, so that we will give the good solution. And alpha k is basically the step length. From here to here, what is the length? It is alpha 1. So this is, and then from x1 to x2 we will go. And from x2 to x3 we will go. In this way, we will go from, this scheme will be the iterative scheme. And in each step, we are trying to find out the best possible solution than the previous one, by giving some suitable direction and the optimal step length. So this alpha k is basically optimal step size. This dk is basically uh, the direction from xk to xk plus 1, right? Now, what is the descent property? The descent property is basically, when we say that the descent property holds, the descent property, we say that the descent, that an algorithm will have a descent property. An algorithm for solving the problem P will have descent property if f of xk plus 1 is less than f of xk. I mean, we are working on minimizing of this objective function, this function f, right? So if in each iteration the value of f decreases, then we say that the algorithm will possess whatever algorithm we are proposing. The algorithm will have the descent property, right? But the basic scheme is basically this only. This is the basic scheme, that we move from one iteration, we move from one point to another point in some direction dk with some step size alpha k, right? uh, what to discuss, Satinder? What to discuss? Which theory? Hello, hello, Satinder. You want me to discuss this thing, basic scheme? Okay. I want to say that basic scheme is basically you are moving from one point to another point in some direction dk, with some step size alpha k. Step size are length between x0 and x1. Similarly, xk to xk plus 1, right? So we say that the algorithm will possess decent property if this inequality hold. That means in each step, the value of the function is decreases. Value of the function decreases, right? Now, next property comes here is order of convergence. So what do you mean by order of convergence? After discussing these basic terms, we will go for some basic methods, that how we can find out the how we can find out at least an approximate optimal solution for a given problem by using these techniques, right? So what do you mean by order of convergence? See, if limit k tending to infinity, norm of xk plus 1 minus x bar, right, upon norm of xk minus x bar raised to power p will equal to some a, where a is between 0 to infinity, right? Then this p is called, this x bar is the actual value of this optimization problem, and these are iterative values xk and xk plus 1. And if this value is tending to some finite value a, as k is tending to infinity, then we say that then p is called basically order of convergence of the algorithm, order of convergence or sequence, or we can say sequence xk. ठीक है, okay. So now let us first go to this technique, which is steepest descent method, right? What is steepest descent method and how it works? Now suppose suppose you are having this minimum fx problem, unconstrained problem, x belongs to Rn, and the basic scheme is xk plus 1 is equals to xk plus alpha k dk. Now, from xk to xk plus 1, as I told you, that there are infinitely many directions. Suppose in which direction one should move so that the value of f decreases. We know that by the directional derivative concept, that the rate at which the f decreases most rapidly is negative of gradient of f. So of course, if we move along negative of gradient of f, then the value of f decreases. So the direction we can choose as negative of gradient of f. And to find out the optimal step size, we will show by an example that how we can find out the optimal step size also. So here dk you can choose as negative of gradient of fxk for this method, right? So let us take one example first of all, and then I will try to explain you this thing, other properties of steepest descent method. Let us take this example fx1 x2 equal to, suppose 3x1 is square. Take any simple example. X1 x2 is in R2. Again, the same problem is basically minimum of f, right? The same problem, minimum of f, right? Minimum of fx1 x2, x1 x2 is in R2. So suppose you take the initial guess as any point. Suppose you take initial guess as 0 0, right? You take initial guess as 0 0. Now you take x1, right? X1. How to find x1 from this scheme? X0 plus alpha 0 d0. D0 will be what? Negative of gradient of fx0. Okay, so this x0 is basically this x0. What is gradient of f? You can find. First of all, what is gradient of f? Gradient of f is simply 6x1 minus 4x2 plus 4, and it is minus 4x2 plus 4x2, right? This is a gradient of fx2, right? Minus 4x2 with respect to x2. It is x1, right? Sorry. Respect to x2 we are calculating. So it is x1 plus 4x2, right? So what is at 0 0? This is 4 0, right? So this is minus of 4 0. So this is minus 4 comma 0. So what will be your x1 now? X1 will be x0 is 0 0, right? Plus alpha 0 minus 4 comma 0. So it is minus 4 alpha 0 0. Now you can put this value here, this value in the objective function to find out the value of optimal value of alpha naught. So what is f of x1 now? What is f of x1 now? So f of x1 will be what? You replace x1 by minus 4 alpha naught and x2 by 0. So this will be 3 into minus 4 alpha naught square. This is 0, this is 0, plus 4 times minus 4 alpha naught plus 6. And this is a single variable function now, so you can easily differentiate it to find out the optimal value of alpha naught. What is f dash? F dash will be your 48 into 2 times alpha naught and minus 16. For maximum minima should be 0, so alpha naught will be nothing but 1 by 6, I think, if I have made all the calculations correct, right? Second derivative is of course positive, means minima, means we are giving in the right way, right? So what is your x1? X1 will be minus 2 by 3 and 0. Right? If you find f, what is your f of x1? You can visualize, you can see f of x1 comes less than f of x0, which is in this case it is 6. So this is the approximation of the optimal solution in the first iteration. Similarly, if one is interested to get more closer and more closer to the optimal solution, then he can go for next iteration x2, and he can find x1 as alpha x1 plus alpha 1 d1, and d1 will be nothing but negative of gradient of fx1 again. Gradient of fx, and this you can find out at this point x1, and again you will find alpha 1, the optimal step length using the same processor, and you can find h2. So when we have to stop, so for stopping criteria, for stopping, we have different criteria. Either people use a norm of xk plus 1 minus xk should be less than epsilon, or some people use norm of fxk plus 1 minus fxk. This mod or norm should be less than delta. I mean, the value of the two consecutive iterations, value of f at two consecutive iterations should be less than some delta. Delta, they give as suppose 0.1 or 0.01, and when you achieve this target, you stop there. Are you getting my point? Is it clear? Okay. So this is a which is basically steepest descent method, right? So we in this scheme we are moving in the direction of negative of gradient of f, as we know that in this direction the value of f decreases most rapidly. We are interested to decrease the value of f. That's why we are choosing this direction, right? And the optimal step size we can find using by simply putting the value of xk in the given function, and you can minimize it, right? Now the next method. Now what are the properties of, first of all, this steeper descent algorithm? Properties of steepest descent algorithm. The first property is that it has a descent property. Of course, it will be having, right? And next is it is globally convergent. It converges globally, and order of convergence of this scheme is 1. Is 1, right? So it's a slow method basically. So now, is there any other method which are available by which we can solve some problems? Yes, we have some other methods also, and one of the method is Newton's method. So what is Newton's method? So Newton method has a faster convergence property, or it converts to the optimal solution most rapidly, because the rate order of convergence of this method is 2. However, the steepest descent method is little bit slow, right? So how we can what is this scheme, and how we can find out the optimal solution in this case? Basically, when you have to optimize this minimum of fx, x belongs to Rn. So we are interested to solve gradient of fx equal to 0 basically, because gradient of at the point where gradient of fx equal to 0, that point will be the point of local maxima or local minima, right? So basically we are interested to solve this equation. So you might have seen Newton's method for equation, right? For fx equal to 0, right? So in the same way, we are having Newton's method in optimization as well. And here this scheme is something like this: xk plus 1 is equals to xk minus Hessian matrix of f at xk inverse into gradient of fx. So this method, this is a iterative scheme basically, right? It is something like you can visualize it something like this. Suppose you have fx equal to 0, f is from R to R, right? You want to solve this equation means in the Newton's method you are having this type of scheme, na? Xk plus 1 equal to xk minus fxk upon f dash xk, I think, right? Right. So here, if you replace this by Rn, so this f dash will become a Hessian matrix. So it is the same type of technique basically, what we have learned in Newton's method, right? But the limitation of this method is that this your Hessian matrix must be invertible. If it is not invertible at each xk, this method is not applicable, right? So let us take one example to solve such problems, basically using Newton's method. So suppose f is basically 8x1 is square minus 4x1 x2. You can take anything. Well, suppose 5x2 square and x1 x2 is in R2. Now you want to solve it using Newton's method, right? Suppose you take any initial point. You take initial point as suppose 1 2. You take any initial point. Suppose you take it as 1 2, right? So what is x1 then? X1 will be x0 minus Hessian matrix of f at x0, its inverse, into gradient of fx0. Now what is gradient of fx first of all? Gradient of fx in this case is what? 16x1 minus 4x2, and here it is minus 4x1 plus 10x2. And Hessian matrix of f at x2 at x, Hessian matrix of f will be what? Will be 16 minus 4 minus 4 and 10. And what is a constant matrix free from x, so you can find its inverse and it is applicable for each xk. So you can simply see that inverse will be 1 by 444, 1 by 144, 10, 4, 4, 16. So what is your x0? X0 is 1 2 minus Hessian matrix inverse is what? 10, 4, 4, 16. It is 1 upon 144 into gradient of fx 1 comma 2. You can put 1 comma 2 here. So it is 16 minus 8 is 8, and it is 1 and 2, that is 20 minus 4 is what? 16. So you can simplify, and what you will get, let us see quickly. It is 1 by 144 and it is um, 5 by 2 plus 1 by 4. So you can simplify it, right? So simplification is little bit complicated here. So see, so I think it will give you 0 0 because this matrix is positive definite. There is a property of this scheme, that is matrix is positive definite, and if it is positive definite, it will converge exactly in one iteration. And you can see that this both are 0 when it is 0 0. I mean, gradient of fx you want to be 0, right? So when x1 x2 both are 0, gradient of fx is 0. So by that theorem, I have applied that theorem. You can verify that this will be equal to 0 0 when because it is positive semi-definite. Because it is positive definite, it will converge exactly in one iteration. So the Newton method is basically, of course, it is globally convergent. Again, this method is globally, Newton's method is globally convergent. Okay, it is globally convergent, first of all. And next is it has a convergence rate, order of convergence is 2. That is faster than the previous method. Okay. So the next method which we are having is conjugate gradient method. What this method is basically. So I hope you understood that what basically this schemes means, or why we are going for this schemes, right? Right? Right. So I am just discussing few popular methods, right? There are many methods of numerical optimization, but I am simply focusing on few popular methods, right? To give an idea of such schemes also. If you are interested, of course, you can go ahead with this topic, maybe in the future, right? So what is conjugate gradient method? Conjugate gradient method is basically a technique, something similar to this technique, this depreciation method, but here the direction is always not the negative of gradient of f. In fact, it is something conjugate gradient direction we see. What is conjugate gradient direction? So first of all, we have to define conjugate directions. So let Q be an positive definite matrix of order n cross n. Okay. Then two non-zero directions. D1 and D2 are called conjugate with respect to matrix Q if D1 transpose Q D2 is 0. No, no, Satinder, you are saying that gradient is 0. It's a settle point. No, no, not necessary. See, we are actually solving the equation where gradient of f is 0, because we are looking at a point where gradient of f becomes 0, right? That will give you the point of local minima or local maxima. Saddle point have some other conditions, right? Okay. So matrix Q, suppose a positive definite matrix, then a direction D1 and D2 are basically called conjugate respect to Q if D1 transpose Q D2 equal to 0. Suppose Q is an identity matrix, then this property means orthogonal of the two vectors, right? Orthogonality. Now suppose you have D1 as I mean vector, and the Q is this matrix. You can take any matrix. Suppose you can take this as a positive definite matrix, right? And D2 is suppose AB. So I can always find AB such that D1 and D2 are conjugate with respect to this Q. How we can find? So D1 transpose Q D2 should be 0. So this implies 1 0, 1 1 1 2, and AB must be 0. So this is 1 0, and this is A plus B, and this is A plus 2B should be 0, and this implies A plus B should be 0. Right? And this is A equal to minus B. So what is the direction basically? D2. This is A and minus A. So you can take direction as 1 as minus 1. So this is a direction which is conjugate, for which D1 and D2 are conjugate respect to this Q. Right? So in conjugate method, what we do basically, suppose you have this problem, minimum of fx and x is in Rn. Right? You have this problem. So in conjugate gradient method, what we do, we start with x1 equal to x0 plus alpha 0 and d0, where d0 I take as negative of gradient of fx0 for the first iteration. In the second, as in steepest descent method, right? In the second iteration, I take x1 plus alpha 1 d1, and alpha 1 I take as a conjugate of d0 respect to Hessian matrix of f at x1. Not understood. I mean, I want to say that I choose this x1 as d1 as, that is d0 transpose Hessian matrix of f at x1 into d1 equal to 0. I choose d1 in this way now. I am not taking d1 as a negative of gradient of fx1 in this case. I am choosing d1 as a direction which is conjugate of d0 respect to this Hessian matrix of f at x1. And alpha 1 I am finding with a similar technique. In the next step again, I will proceed the same way. And actually this method is faster than the steepest descent method. That's why people are using conjugate method to find out the optimal solutions. Not clear? Is it clear or not clear? Okay. Okay. So in this way we can find out. Again, the stopping criteria will remain the same. Stopping criteria will be either where to stop. So stopping criteria will remain the same. That is either norm of xk plus 1 minus xk is less than epsilon, or norm of fxk plus 1 minus f of xk should be less than delta. It is stopping criteria remain the same. So any doubt up to here? So Satinder, we can know that it is faster because we have theorems, right? By theorem we can prove it, that the rate of convergence of this is more than the rate of convergence of the steepest descent method. Okay. Any other question? Yes. So Now, what are direct search methods? Just give an idea of direct search method. For it is applicable for unimodal minimum functions. So, what are unimodal minimum functions? First of all, these are those functions which has only one peak, right? The functions which has only one minimum point is called unimodal main function. Similarly, we can go for unimodal max function also, right? Now, if you have, I mean, this type of function which has only one minimum point is called unimodal minimum functions, right? Now, if you have a min function like this, basically what we do, we start with some interval x1 and x2, suppose, right? And we try to reduce the width of the interval by some direct schemes like Fibonacci and Golden search methods, right? Line search techniques. So I'm not going to detail of these techniques right now because of the time. I'm just giving you an idea that if we have interval x1 to x2 or a to b, for example, suppose we are having a to b here, right? We always try to reduce the length of the interval and try to make it closer and closer so that the minimum point will always lies inside that interval, right? And for to reduce the width of the interval or the length on the interval, we have different algorithms, right? The basic principle involved in all the algorithm is this, right? Suppose you have, this is your A and this is your B. And some by the method of algorithm, you find two experiments in between x1 and in between A and B. Suppose this is your x1 and suppose this is your x2. And fx1 is supposed less than fx2. Initial interval is your A to B. Initial interval is A to B. We are minimalize. Aim is to reduce the width of the interval, right? Okay. Satendra, I will come to this problem after this discussion, right? What you want to say, let us discuss this thing after this, right? So now fx1 is less than fx2. So now which is the interval in which minima lies? So minimum lies in between A to x2 now. You might be thinking, why not x1 to x2? Because this x1 may be here also. Still fx1 is less than fx2. But it is guaranteed that A to x2, if x1 is less than x2, A to x2 minimum will lie, definitely. However, if fx1 is more than fx2, suppose this is your A point and this is your B point, and this is your x1 and suppose this is your x2. And minimum is here. So where minimum will lie now? Minimum will lie from x1 to B. Why not from x2 to B? Because x2 may be, see, here a minimum is not there, right, in x2 to B. If x2 is here, we cannot say from x1 to x2. So, but from x1 to B, minimum will always lies. And if both are equal, so in this case, fx1 is more than fx2. If fx1 is equal to fx2, then minimum will lie in between x1 and x2. So these are the fundamental, scheme which we apply to find out the to see that what is the next interval of uncertainty. These are called interval of uncertainty because we are not certain where minimum is, but we are trying to make it interval smaller and smaller, so that at least we can find out the approximate value of the optimal solution. Yeah, Ajay, what is your question? No, for Ajay, for if problem is positive definite, it is always globally convergent because of the convexity property. If it is positive definite, this means function is strictly convex, and this method is globally convergent, right? And Satyendra, what is your question? For D1 to D2 135 degree, how direction is helping in optimizing? And direction plays an important role in optimizing because I told you that in which direction one should move so that it is optimal. I mean, in which the value of f decreases. That's why, right? So, any other question, please? We stop here. Any other question? So for unimodal function, we have different techniques, different line search methods like golden section method, Fibonacci method, right? Dichotomous method. So those methods basically work on this scheme only, with the scheme which I discuss here for unimodal functions. The scheme is different, but the method is same, right? Yeah. Okay. Any other thing you want to know, or any doubt you are having? Any doubt? Yes, Brinda, any doubt? Okay. So this is simply a brief introduction of search techniques, right? So if you understand this thing, then you will understand the other schemes also. And using those schemes, if you are using, or if you want to use in your problem, the problem in which you are studying, then you can learn it easily using these basic fundamental things, right? So no other question? Yes, if you remove the condition of convexity, then there may be a problem. Right? Right, Ajay? Satinder, what happens that suppose you are solving a research problem, right? And you encounter a optimization problem which you want to solve. I mean, you have modeled something, and after modeling a problem, you encounter with the optimization problem, which you find out for which you want to find out an optimization optimal value, right? Now you have seen the literature that what analytical methods you can apply. You search for analytical methods, but because of the complexity of the problem, it is difficult to apply. Then you go for search techniques, right? And in search techniques, you can use some algorithm which is available, and you can at least find out the approximate optimal solution of a given problem, right? So basically, we should have an idea of such problems because these problems are frequently used in many research problems. Those research problems may have some real world application as well, as you said, right? Any other thing?
Okay, thank you, Dr. Shiv. Thank you, Professor Shiv, for your nice lecture. Question from participant side. Okay, thank you, Professor Shiv Gupta.
Thank you. Thank you. So thank you very much, everyone. Right? Thank you.
Okay.
Thank you, Professor Gupta.
Yeah. Thank you, Rahul ji.
Yeah, on the behalf of the organizing committee of the FDP and on my personal behalf, I express my thanks and my gratitude to you for delivering wonderful talks in our FDP. One or two students are writing about books also. Can you please suggest some books? This is the chat window comment from the
Yeah.
participants.
I'm just writing the books in the chat window itself.
Yes, please take your time.
Yeah. So for such problems, you can have numerical optimization by numerical optimization with applications, something with applications. By Chandra et al. There are basically three authors in this book. This is Chandra, Jayadeva, and Mehra. This is a good book, right? There are many books on this topic. You can also see Bazara and Sharari. See.
Yeah, thank you.
Yeah, just I'm sharing other book also.
Thank you.
This is Bazara and Shetty.
Professor.
I'm just writing here. This is Bazara and Shetty. Bazar and Shetty. These are the authors. Bazar and Shetty, and book title is Fundamentals Introduction to Optimization, something like this, an introduction to optimization. So Bazar and Shetty is also a good book on optimization, and from which you can see some of the concepts of convex functions, and it is basically on non-linear programming problems. And one Bazara Shirari is also on LPP also, right? If you're interested in linear programming problems, for linear programming problems, you can see Ravindran Phillips. For LPP, this is not LOP, this is LPP. For LPP, you can see a book by Ravindran Phillips. This is something introduction to linear programming problems. Something might be a title. When you search, you will get. When you write Ravindran Phillips on LPPs, you will get the book. Right? So these are few books basically which deal with optimization. I mean the topics which I have covered. So thank you very much. Rahulji, thank you.
Yeah, thank you, Professor Gupta. And it was indeed a pleasure to have you here. And I hope that participants must have enjoyed the lecture. They have gained knowledge also about the topic which you have covered. And Professor Gupta, one request to you, please send me the PDF files of your PPTs or any other course material which you would like to
I will share
with our participants, so that we will be uploading on the Canvas platform, and the registered participants can again go through the notes also, as well as the recording of your lecture also.
Okay. Thank you. I will share.
Yeah. Thank you.
Thank you, Rahulji. Then thank you very much.
One announcement for you. Yeah. Participants, I would like to make an announcement to you. We will be having one quiz now from 6 to 12 p.m. You may choose any 1 hour to solve the quiz. There will be only 20 simple multiple choice questions, and only one answer will be. I have sent an email to you regarding this. You can log in your Canvas platform, and then click on the quizzes tab, then take the quiz 1 and solve it. You can choose any 1 hour and in between 6 p.m. to 12 p.m. today for the quiz 1. Similarly, for the quiz 2, it will be available from 9 a.m. to 3 a.m. Though we have a lectures from 9 to 11. Tomorrow from 9 to 11 that you have to attend. So in principle, you will be having time from 11 to 3 to solve the quiz number 2, which will also be having another 20 questions, and quiz number 2 will also be for 1 hour. Whenever you will start on the quiz, your 1 hour time will start from that instant. Okay. Once the 60 minutes are completed from that instant, it will be automatically closed. Okay. So as per your convenience, you may choose any 1 hour in this time window which we are given to you. Like today, time window is from 6 to 12 p.m. in the night, and tomorrow time window is from 9 to 3 p.m. And you have to attend the lectures also. We have only 2 lectures tomorrow from 9 to 11. It is on multi-objective optimization, neural networks and their applications by Professor Manoj Thakur from IIT Mandi. Quizzes are simple. You can please don't take any tension about the quizzes. You can easily solve that, and we will be taking best of the 2 quizzes, and 40% marks is required to qualify the quiz. Okay. If you have any issue, any problem while solving the quiz, like suppose your you are facing some issues, you may always write on the WhatsApp. My students are available, they will help you, okay, about any technical glitch or any technical issue. One thing, because it's a time-bound quiz, so your time in Canvas platform, the setting of the time should be daily time zone, okay, otherwise it will give you an error. When you will start solving the quiz, it will give you an error. So make sure that before starting the quiz, your time in the setting of the Canvas platform should be daily time zone. Then there will be no issue in solving the quiz. If you have any doubt, any question, you can write here in the chat window. I'm giving you another 2-3 minutes. Please write to me if you want to have any clarification on this. Yes, yes, Satyendra. The syllabus for the both the quiz will be same. Whatever the our speakers have covered, the syllabus will remain same. There is a 2 quiz. It's like I'm giving you option, and the best of the 2 will be taken, and in that you should be qualifying. Like the qualifying marks will be 40%. Okay, so each question will be having 1 marks. So it's a 20 questions. Then 20 means you should get at least 8 marks. Then you will be able to qualify the quiz. I'm again wait 2-3 minutes. If you have any question, you can